get started. Before we do, though, I thought I might try something from the command line. No guarantee this works. This is a terrible idea in practice, so I'm actually going to run some performance benchmarks while I'm going to do my presentation, so you can see the results at the end. Cross your fingers and hope it works. It's a terrible idea because I don't have enough time to up the iterations enough. But also, of course, the presentation is going to be using graphics and all that stuff. It's going to suck up CPU and memory and detract from the results of the benchmark. But I'm going to do it anyway, just because. So I'm John DeGoes, and I want to thank all of you for the opportunity to be here and to share some of the work that I'm doing on the Scala Z8 effect system. This is what we're going to talk about today. I'm going to do a little bit of an intro to the talk, and then I'm going to give you a pretty complete tour of Scala Z8's I/O. And we'll talk about some of the core combinators that you can use to build very rich, purely functional applications. And then we're going to do a little bit of a versus. I'm going to talk about one implementation, Future, and Cat's I/O, and Monix, and Scala Z/I/O, and all this stuff, and compare them from a variety of angles. And let's be honest, that's what you came here for. There will be blood and guts, and you'll be able to take screenshots and post it on Twitter and all that stuff. Probably say some stuff to get me in trouble. And then I'll just go ahead and wrap it up at the end with a few closing thoughts. So I like functions a lot. I program with functions. I contribute types and functions to open source projects like Scala Z8. And I start companies, actually 2 companies so far, powered by functions. I'm one of those crazy functional programming zealots that you read about. In fact, you may have read about me. I rant against nulls and exceptions, partial functions. I rant against pattern matching, data structures, and even if statements. I basically rant against everything that's not a function. But as much as I believe in the power of pure functional programming to change the industry, and as much as it's changed my own sort of personal programming life and professionally, it's time for a little bit of a reality check. Some straight talk here. How many of you do pure functional programming in your day job full-time? So it's basically the people who work at my company plus a couple other people. So lots of hands did not raise. Like, ideally, everyone's hand should have raised. Everyone should have been like, yeah, me too. But that didn't happen. Why? Well, it's a reality. Most Scala programmers out there don't program functionally. Can't deny that. In my opinion, it comes back to the fact that functional programming, the way we talk about it and the way we sell it to people, we use words like type safety and equational reasoning and referential transparency and abstraction and so forth. And a lot of these are concepts that directly benefit you as a programmer because they simplify the way you reason about software. They help you jump into a code base and understand it and so forth. And they help you produce software with fewer defects and whatnot. But these benefits, they directly benefit you, but they only indirectly benefit the business. That is, it's hard for a business to measure the impact of your ability to do equational reasoning on your software. And that's not true for all the different libraries and languages and tools and techniques out there. Some of them actually directly benefit the business. So libraries like Akka and so forth that provide sort of features that address real business pains right now, today, that they can then turn around and sell, that generate revenue. Those are the kinds of things that businesses are really, really interested in. And ultimately, like anything that directly benefits you as a developer, is going to indirectly benefit the business. It's just harder to show that. It's harder to see that. I want companies pounding down your doors and saying, you gotta be checking out this functional programming stuff because it will change the way we write software. It's going to allow us to ship more faster. And that's not happening. And conversely, anything that directly benefits the business is ultimately going to indirectly benefit you professionally. If the business is doing well, it's going to be good for your career and stability and give you bigger budgets and all that stuff. But where you really want to be ideally is that sweet spot of languages and tools, libraries, features, and so forth that directly benefit you as a developer, but it also directly benefits the business. So let's go ahead and take a step back and throw all this FP stuff, equational reasoning and type safety and so forth, let's throw it all out the window and talk about a business scenario. So in this business scenario, we've got a little web server we're developing. And it's got to service, thousands, tens of thousands of requests per second. And it's very complex. It's a typical microservices-driven architecture. It's built like Amazon and lots of other companies are building software out there. And it gets in a request, and it's got to parse it, and then it's got to do a whole bunch of stuff. And based on that stuff, it's got to do even more stuff. And one of the most important things pervasively across all of business is keep that latency down. Like the difference between 200 milliseconds and 1,200 milliseconds is millions of dollars. You can measure that in lost revenue. So as a business, we care about keeping that latency down as tight as possible, which means we want our software to be very, very fast, but we also want to be able to take advantage of multiple cores. We want to be able to do as much in parallel as possible so we can compress that window of latency. And we want to make sure that that server runs solidly. We don't want to be leaking resources and having servers falling over in the middle of transactions and so forth, because again, that costs tens of millions of dollars for a retailer. These things can be measured, and businesses really do care about them. So let's say something fails in this big, elaborate process of ours. We have a few things that succeeded, and then this SQL query over here fails, and all this other stuff is in progress. What we want to be able to do is shut down everything that is no longer relevant. We determine we can't satisfy the request, or the request is not valid, or we just short-circuited a bunch of stuff and we're able to break out of there early. We want to be able to stop all the other dozens of other concurrent requests that are in process executing. And we want to do this because we don't want to waste resources. We want to make sure that we do the minimum amount of computation possible on every node of our web server cluster, so we can make sure we get the most bang for the buck. What are the types of business level pains that we would have to solve if we wanted to do this in a reliable, robust way that would make the business happy? Well, we're going to have to deal with asynchronicity because blocking doesn't scale. It sucks up resources like crazy, so we're going to have to write our code asynchronously due to limitations in the JVM, the lack of green threads, as Daniel pointed out. We're going to have to suck up all the cores available. We want to max out all our cores and do as much work as possible in parallel to compress that latency. We never want to leak a single resource, no matter what. Like, you leak one thing one time, and that becomes many things over many times, and eventually you bring the server down. It's going to get slower and slower and slower. That's going to increase latency, and eventually everything's going to just fall over. And finally, we want to do all of this with high performance. We do not want to compromise our performance. That's where Scalaz 8 effect can help us. What 8's effect system is it's a very small, very composable set of data types and type classes that help programmers like you and me trying to solve business problems to build very principled, performant, and pragmatic I/O applications that don't leak. They don't leak resources, they don't block, and they execute concurrently. In other words, they help developers like you and me add value to the business. And the heart of Scalaz 8's effect system is a data type called I/O, which you just learned about from Daniel. And what I/O is it's nothing more than an immutable value. This is a data structure. It's an immutable value. And what it does is it describes an effectful program. And this program will either produce an A, it'll fail with some sort of throwable, or it will run forever. That's all it is, a data structure that describes an effectful computation. So all these methods that we're going to talk about in a few minutes here, they're just going to be functions that take one I/O and return another, just like all the functions on the list. They take one immutable data structure, they return another. Scala's at 8 I/O, it helps you quickly build asynchronous, concurrent, leak-free, performant applications, which coincidentally, or maybe not, happen to be type-safe, purely functional, composable, and easy to reason about. That's not the reason you tell your boss for using this library. That's the reason you use it. But you tell the boss that it's about all the above stuff. So let's go through the building blocks in Scala Z8 to give you a feel for, first off, what they look like, and then second off, how you can use them to build ever more powerful things. So what I'm going to do is I'm actually going to cover all of the core primitives in Scala Z8. There's only a few of them, but I'm going to do more than that. I'm going to show you how we can take these primitives and we can build other cool stuff on top of them. So pay attention to the examples. They're not just examples. I'm actually going to be building on them to build up some really cool stuff that we'll talk about close to the end of the talk. If we're using 8's I/O, how do we build an application? Well, it's not that much different than the example in Haskell that Daniel brought up. You extend safeApp, and now your main function just returns I/O of unit. So you don't have to call in safe perform I/O or any of that stuff. You know you're building a main function that is going to return I/O of unit. And this is a little example program that does nothing more than ask what your name is, it reads a line of input from the console, and then it prints that back out to you. And note, this looks just like any other imperative program you would write, plus or minus a few syntactical changes. So yes, you have to get used to this little for notation, but if you're using future, you probably already are aware of that notation and know how to use it. So just small little change like that can enable you to shift over from whatever imperative code you're using now to Scala Z8's I/O and capture all the benefits that we'll be talking about. Pure values. So if you want to take a pure value and lift it up into an I/O program, you call this apply, which is otherwise known as point or pure. Don't use this for effects, by the way. This is only for pure values, lifting pure values up into I/O programs. If you want to create a program that represents failure, you use the fail primitive. And you provide an exception, and that program represents a description of a program that fails immediately with the specified exception. If you want to recover from a failure, you use the attempt combinator, which is defined directly on I/O and allows you to take an I/O of A, and if there's any error in that computation, if there's any failure, it allows you to surface that error up into the value level where then you can recover from it and deal with it as necessary. If you don't want to deal with your errors, of course, don't use this, but if you do, if there is some way to recover from some sort of runtime exception, then by all means use the attempt combinator. And this little weird symbol here, that's Scala Z's either, otherwise known as disjunction. And I know what you're thinking, why the heck are they using ASCII characters here? And I'm thinking it too. It's terrible, they should be using Unicode symbol right there. Maybe an 8. So if attempt takes an I/O of A and surfaces a throwable, a potential throwable in a disjunction, then absolve, IO.absolve, is the undo operation for that. And it takes something that's an error, a potential error that's been surfaced, and it submerges it into the computation. It's a natural undo, and we're going to see an example of how this is used later. To import effectful code, so you're dealing in Java land or impure Scala land, and you want to import an effect into I/O, you use the sync primitive. And here's an example of creating pure put stir line and get stir line functions just by wrapping up all the stuff in Scala. Very easy to do this. And here's that little program that I gave you earlier. You can see how you can use these custom-defined pure effectful functions in your own software. The asynchronous import is a bit more complicated. And actually, this is a point of difference from Scalaz 8.io versus all the other implementations out there. Like all the other implementations, the constructor for this async primitive, it takes a handler that is going to accept a callback. And that callback, you can either feed it an error if the computation failed, or you can feed it an A if it succeeded. But note here, the major difference between this and Scalaz 7's task and CatIO and so forth is that instead of returning unit here, the handler itself returns an async result. This is a subtle but extremely important difference between 8.io and everything else out there. The difference is async result can represent one of three states. It's a sum type. It can represent the default in other libraries out there, which is a promise that the callback that you send to this handler will be invoked at some point in the future, and that's called later. So if you return that from your handler, that means, okay, I've done whatever async effect I'm going to do. I'm going to call your callback at some point in the future. But you can also return a different constructor in that sum type called now. And that represents the act of computing a value right now and not later. In this case, you're going to ignore the callback. The handler is going to ignore the callback. It's going to immediately return the value. And the reason for this constructor is that it's very common to be in the situation when you're trying to write really high-performance code where you need some effect type, but you don't know yet if it's going to be synchronous or asynchronous until you start executing the effect. And what this constructor allows you to do as a library author is do some imperative code and figure out whether or not you have to use a callback or whether you can return something right away. And this allows you to dramatically improve the performance of code, because anytime you have to use callbacks, anytime you have to use a real async block and you have to invoke the callback and do all that stuff, that's a lot of ceremony and it's a lot of allocations and it's a lot of overhead. And purely asynchronous code that's driven entirely by callbacks is really, really slow. And so this constructor basically allows you as a library author to say, okay, in every circumstance in which I can avoid constructing one of these async data structures, continuations of my program that use callbacks, I'm going to do that. And so it represents a way to short-circuit this and say, okay, as I'm executing my effect, I've determined I can actually give you a value now. Maybe some value is in the cache, or maybe some computation succeeded. I got the lock, or whatever it is, and you can return that value now. You can safely ignore the callback. At the end. And then now, or maybe later, is the final constructor in the sum type. And this is extraordinarily important for resource-safe applications. And what it represents is, it represents your commitment to eventually call the callback later. So you're going to call it. You can't compute the value now, like the now constructor. You're going to call that callback. But also, you're going to provide a way for that asynchronous computation to be canceled, to be interrupted. And this is enormously important for a huge host of reasons. For example, you're doing autocomplete in the browser, and you want to be able to interrupt a lookup, which is a costly operation. Like, you want to be able to kill these long-running server processes that are returning streaming results as the user's typing more characters, because you want to feed the latest information to the server. Or you're invoking some API, and that API takes a long time. Like, it takes 900 milliseconds. And then you decided you didn't need it. So just close the socket connection. Like, there's no need to actually keep that socket connection open, consuming a resource, sucking up a thread, reading data, consuming, who knows, megabytes worth of information in that 900 seconds. You need a way to be able to safely terminate that. And this constructor allows you to precisely specify the means for the runtime system in Scalaz 8 to be able to cancel that computation for any asynchronous computation out there. And then a final example, which is very, very common, is you want to be able to do something a second from now or 10 seconds from now, or you want to be able to repeat it. But obviously, if you interrupt that computation, if you no longer need its results, then you don't want to have to keep that in the scheduler and in the runtime, consuming memory and threads and all that stuff. You're going to fill up your system with your scheduler with useless crap that doesn't need to be invoked, and then you're going to be running computations that don't need to be run and doing all these effects. It leads to leaky applications. So let's actually use the simplest of these constructors, the later one, to build two different combinators. Let's just show you how they work. Spawn, which does nothing other than take a computation and execute it off on Java's default thread pool. And how you do that is you use the async constructor, and you provide it your handler, and then you're passed in a callback, and your job is to invoke the callback. So you call the default thread factory to create a new thread, you pass it a runnable, and then you call the callback with the result of evaluating that A. And then in the async return, you use the later constructor that promises it's going to eventually call the callback. The other combinator is called never, and never does exactly what you think. It's the equivalent of while true empty braces, except it wastes a lot less CPU power. And what that does is it says it's going to return some value, any value. Never of A promises to be able to return anything at all, and it never actually does anything at all. So that's a computation that will never terminate. So here's a little example. Once we wrap up our asynchronous effects, like Daniel showed with Scalaz 7 task and CatsIO, it becomes super simple to use these things, just as if they were ordinary synchronous values. And like CatsIO, Scalaz 8IO makes the decision to allow you to seamlessly combine synchronous effects with asynchronous effects. And the syntax looks the same from your point of view. There's no difference. You can't even tell. And indeed, the only reason why we have asynchronous effects at all is because there are no green threads. It's an implementation detail. It's a way to save a few CPU cycles so you're not spinning, blocking on threads. So fundamentally, though, there's only one concept there, which is the concept of computation. And it's merely an implementation detail, whether that computation is purely synchronous or asynchronous. So that's why both of these libraries have chosen to unify these two seemingly different effect types. Another primitive is sleep. And sleep does exactly what you might imagine. It creates an IO of units that will be invoked the specified duration later. This is how we would use it. In a simple example, we say time to sleep, then we sleep for 10 seconds, and then we wake up. And like all of Scalaz 8IO, it doesn't matter if something looks like it's blocking, it's never going to block. There's absolutely nothing in 8 that blocks. Everything is totally asynchronous. So this is not actually sleeping, of course. It's scheduling this to be run later. And with a sleep primitive, we can build this really handy delay combinator that is defined on I/O, and it can take that I/O of A and it can delay it a certain amount of time into the future. And we might use this like put stir line, delay 10 seconds. And this should show you here, or at least start to give you a glimpse into the power of reifying computation. What I/O does is it says, instead of writing our programs as statements, which are not first-class things, there's no such thing as a statement in your program. You can't pass blocks of code around, and you can't combine them. You just don't do that. It's not first class. We take it in functional programming, we turn these statements, these blocks of code, into values, computations, IOs of A. And as values, we can put them in data structures, and we can pass them around from program to program, and we can combine them together, and we use them just like collections. IO's nothing more than a data structure. So here, we take the put stir line, and we print that, and then we call delay. That, of course, creates a new IO computation. Like, we're not changing anything. This is totally immutable data structures. And then we delay that for 10 seconds, and we get the composition of those two programs. And that's what we can then end up scheduling or sequencing into the main thread of our application. So that's synchronicity and purity and failure and asynchronicity. But what about concurrency? So this is one of the areas where Scalaz 8 takes a different approach from cat's.io and says, we're going to give you concurrency primitives because we know you're going to need them anyway. You can't write programs without concurrency. And also, we want to make them super fast, so we want to highly optimize embedding them into the runtime system for the I/O monad. And also, we want to bake in very strong guarantees about what these concurrency primitives can do. So strong that it would be hard to implement them off in a separate library that's not part of your runtime for the I/O. At least it would be hard to do that in a performant way. So we have our choice, though. There's lots of different concurrency models that we could look at. We could use threads. That's the Java approach. We could just have a straightforward one-to-one mapping of threads in I/O to threads in Java. But these are operating system level threads, and they're very heavyweight. Also, you can't program them with features that you might want to have, like you actually can't safely kill a thread. The most you can do is interrupt it, which will cause an exception to be thrown from any point at which it's blocking. So that gives you one way, but it's not safe. You know, it's in general not safe, and it's not reliable. You can't rely on the fact that your users are blocking in order to be able to cancel unwanted computation. So that's not great. Green threads, in theory, would be awesome. But you can't do that because those are built in at the language level. Haskell can do that, but we can't do that. So how about something else? How about fibers? Fibers are a very, very powerful concurrency primitive that allows you to disconnect the concept of an independent thread of execution from operating system level threads. You can have fibers in JavaScript. You can have hundreds of fibers or thousands of fibers, whatever you want. They're at the application level, which means they're tractable. For us writing libraries like Scalaz at 8, we can actually solve this problem. We don't have to mess with the language. They're very, very lightweight. You can have, millions of these things in a single server, executing concurrently to different degrees and blocking on different stuff. And also, really interestingly, is we can get them for 0 cost in a pure functional program. And the reason for that is pure functional programs written in I/O, they have to be interpreted into the effectful world. So they already have a runtime system. And we can throw other stuff in there at no cost. And in fact, not only do fibers have no cost for pure FP applications, but we can define their semantics. We can add whatever we want. So we want a way to prevent excess wasted computation and to guarantee safe release of resources and all that stuff. We can do that with fibers. So in my opinion, you're going to see a lot more frameworks and libraries taking that approach and moving towards fibers and away from threads because it solves the business pains in a way that's tractable. So fibers, we want fibers, but what concurrency primitive are we going to use? If only we could turn to some well-known Scala expert who might be able to give us a clue about the right concurrency primitive here. Fork join. Daniel Spiewak himself said it. So fork join, and the really amazing thing about fork join is fork alone is insufficient. It's not enough. If you build a framework with just fork, you find yourself in a situation where you're writing lots of unnecessary code because sometimes you want the value from your fork fiber, but also you can't define that in a lawful way. Fork doesn't mean anything. Once you add join in there, you can suddenly start defining algebraic laws for these things, and things get really interesting. So the basic idea is this. On any I/O of A, there's a method called fork, and that forks off an independent fiber. And that executes in a fresh stack frame. And what it does is it gives you a handle to the fiber. It gives you a fiber of A. So you fork something and you get a fiber of A. And then what you can do with that fiber is one of two things. You can either join it, which is going to give you the value from the fiber in a non-blocking way, of course, or you can interrupt that fiber with some exception. And Scala Z8IO has very fine-grained interruption semantics. And they are defined as follows. Every single flat map that composes the chain that defines your fiber, I mean, basically every fiber is a long chain of flat maps, at every single bind point, it checks for interruption. So if you want to interrupt something, you can interrupt it at the level of the statements in your functional program. There's no wasted computation. And if perchance you happen to be inside an async computation, you're right in the middle of a statement. And how are we going to deal with that? Well, when you created that async computation, you specified a canceller. So we're going to invoke that canceller, which means that 900 milliseconds of reading a 2 megabyte file, it's gone. No overhead. Or that look-ahead form that you're building in Scala.js, cancel all those old requests, don't take up socket connections, don't take up server CPU and memory. Get rid of those computations because you don't need them anymore. These are very, very powerful primitives. And in combination with a few other things that we're going to see here in a second, they allow you to build applications that are very concurrent, very performant. They're resource safe. They don't leak resources. And you can also reason about them with all the great power of FP. Here's a little example of showing you just how easy it is to use these fork-join combinators in defining a concurrent version of Fibonacci. And it just forks off the two child things and joins on them, which is non-blocking, and yields the result. So I said a moment ago we need a few other things. We need, actually I think this is just two more primitives. And one is this race with function. And it's a generalization of the race function or the whatever it's called in future, first success of, or it's the one that starts a bunch of things off and it's going to choose the first success. That's actually, it always bugged me, the type signature of that. And the reason for that is you look at IO of A to IO of A to IO of A, and who knows what that means? I don't know what that means. Does it return the first one? Maybe. Does it return the second one? Does it return neither and fail? Who knows? Like you can't really gain any great insight into how that function behaves, and people who have tried to write laws for that have by and large failed and given up. It's just not specific enough. There's not enough meat there for you to be able to reason about that either by looking at its type or in algebraic laws. And so it turns out when you have a first-class concept of a fiber, you can define this much more powerful general-purpose race with. And what race with does is it takes the this thing, it's defined as a method on IO, so it takes the this thing and some other thing that, and it kicks them off. And then what it's going to do is either the left-hand side is going to finish with the value first, in which case you'll get an A and a fiber of B, or the right-hand side, which is an IO of B, is going to finish, and you'll get a B and a fiber of A. And then you specify a function for combining whatever you got there into an arbitrary type IO of C, and it's going to return the IO of C. So if you're used to reasoning about types, you can look at this and you can know what it does at a very deep level, because the types are so parametric here that there's no choices. It has to do what it says it does. And it turns out this is powerful enough to implement the ordinary race very simply and in a way that's 100 times better than the other races that you've seen out there. So in this one, we define race as this race with that, and then if the left side won, we interrupt the right side with an error saying you lost the race. And then we produce the A. And on the other hand, if the right side won, we interrupt the left-hand side with an error saying you lost the race. And then we produce the A we got out of the right-hand side. So what this does is it means you race two things in parallel, and when this one produces a value, You can chop off all the rest of that computation and throw it in the trash can. You're not going to be wasting your CPU and your memory and your sockets and your file handles and all that other stuff. You're not going to waste all those resources, network resources and memory and CPU, on all this unnecessary, unwanted computation. It's gone forever. This is a safe, resource-safe version of erased. Defined, we didn't even have to bake it in. It's just defined in terms of a much more abstract general purpose concept. In fact, we can also use this, the derived erase, to implement timeout, a non-broken timeout, which is unique because most timeouts out there are actually broken. So we specify a duration, and all we do really is we produce an error saying we reached the specified timeout, and we delay that into the future. And then we take that and we erase it with the computation that we're timing out. And then one of those is going to finish first, either the timeout, because it took too long, or the computation will succeed and the timeout's at some point in the future. And then we end up chopping off the other one and throwing it away. So because of the semantics of erase here, we're able to build a non-leaky timeout. As soon as we time out that big, long I/O computation that's reading megabytes and megabytes, it's gone. It terminates the socket connection. It's done. You don't have to worry about it. Or conversely, if the timeout lost, then we remove it from the scheduler, and we're not piling up lots of unnecessary things in our scheduled executor. We just get rid of it and don't have to worry about it anymore. And in fact, this race with primitive is so powerful, we can define par with it, which is a primitive that takes two, an I of A and I of B, and it returns an I of A and B. And there's only 4 cases we have to handle. It's pretty simple. Either the left one succeeds. Well, what we do is we attempt both sides because we want to see the errors. Because even if the left finishes first, we don't necessarily want it, because we want the first value we need values from both sides because it's par. So what we do is we make sure that if we get a value from one side, we resume the fiber on the other side. We join it to get its value, and vice versa. But if we get any error from either side, we interrupt the other side, which means that par is resource safe. If you're doing 100 things in parallel, and one of them fails early on, there's no need to do 99, for another 2 minutes. You can kill them all. They're all gone. And that's remarkable. As far as I'm aware, there's no other library that defines it like that in a way that's safe, resource safe. So we also have this wonderful mvar here, which, unlike the one in 7, is not broken. And it is very fast, very efficient, non-blocking, 100% asynchronous, and takes advantage of the constructor for async to do synchronous computation whenever possible. If this mvar can succeed synchronously, it will. So it'll be really fast. And it's only in the case that it cannot possibly succeed synchronously that it's going to do async. And an mvar, for those of you who don't know, it's a concurrent variable that is either empty or full. And those are the only 2 states. If it's full and you try to put, then it blocks. Not blocks in IO's case, it actually suspends. Same idea. And then if you take when it's empty, it's also going to suspend until someone puts something in there. And then there's miscellaneous functions like try, which will return instantly always. They may not do what you wanted to, but they'll return instantly. So very fast, low-level concurrency primitive here. And you can actually implement a heck of a lot with mvar. Like, you can implement queues and channels and almost everything that you would ever want to implement, you can implement on top of this. It is a bit too low level. And here's a very simple example where I create an empty mvar, and look at how easy multi-threading is. Like, it's just so seamless. Like, here I actually have 2 different fibers, and there's no ceremony, there's nothing. Because these IOs are just values, first-class values, creating that fiber 2 here, I create the empty one, Then I put a var, but I forked that, so that's another fiber. So in a different fiber, it's putting something into the var, and in the main fiber, it is taking something from the var. So what happens is it creates the empty one, and then it forks this thing over here, and it takes. And this take is going to suspend until something's put into it. But over here in this other fiber, it's going to put something into the var, and then so it's going to resume instantly. Well, more or less. But as handy as mvar is, and as useful as I think it will be to solve your real-world concurrency problems, I'm a huge fan of STM because it allows you to very cleanly, declaratively solve nightmare scenarios, or they would be nightmare if you were using blocks and so forth. You can just easily express their solutions using a small set of combinators. And so as part of Scala Z8's effect system, what I want to do is build a real STM that works like the Haskell version of STM, which is unique because we have a few STMs in Scala. There's one open source one, Akka has one, and so forth, but none of them obviously cleanly integrate into I/O, and none of them have the same semantics as the Haskell version. All right, a couple more combinators we're going to cover real quick. You've seen to date here that if you fork a fiber, you can interrupt it. And that should trigger danger flag in your mind. Well, what if I don't want it to be interrupted? Remember, we interrupt at every bind. So in between all the statements of your program, those are the interruption points. There's a lot of interruption points. We can interrupt anything, anywhere, and save a lot of unnecessary computation. But what if you have a critical section that doesn't want to be interrupted? You can't afford to interrupt it because it's doing two things. And those two things have to both be done together or not at all, unless it crashes, in which case, who cares? And for that, there's this uninterruptible combinator that defines a critical section. It's defined on I/O, so you take an action and you just call uninterruptibly on it. And now, that I/O program, it can't be interrupted. It can be interrupted before it enters that section, and after, but not in between. And this has the compositional semantics you would expect. So if you have an uninterruptible section embedded in another uninterruptible section, then the whole thing is uninterruptible. I urge you not to use this because first off, you make your programs more prone to leaking resources, but it's not a very robust way of handling most things. But if you need to, you can use it. What I prefer and encourage you to use instead is the second to last combinator in Scala Z8, and that is our primitive. It's called bracket. And this is a very robust, sort of bulletproof version of try, catch, finally for the I/O monad. And what it allows you to do is guarantee no resource leaks ever. And it does that. It's defined on I/O, an I/O of A. So your I/O of A represents acquisition of an A resource. And if that computation succeeds, it's going to produce an A, of course. That's your resource. So bracket lets you specify a release that takes an A and returns an I/O of unit, which it represents cleaning up the resource, closing the file, closing the socket, deleting some information from a cache. And then the final action that you pass in here takes that A, that file, socket, whatever, and does something with it, produces an I/O of B with it. And then the bracket combinator as a whole returns that I/O of B. So this is one of the primitives that's baked into Scala Z8, so you have a strong guarantee that if your acquisition succeeds, release will be called under all possible circumstances. And that includes, by the way, interruption. So if you've opened a file and you're reading it and processing it and parsing stuff, and this is taking minutes, who knows how long it's going to take, and that's interrupted because it was forked by some other fiber, then what's going to happen is that computation in the middle, the use will be interrupted, but then on the way out, release will be called, and all the resources of that will be safely released. So if you use this every single time you acquire any resource in your application, then you have that guarantee you don't have to worry about resource leaks ever. And part of the semantics of bracket is that acquisition and release are atomic. So you don't have to wrap those in uninterruptible or anything. You already have that guarantee. In general, you don't want to interrupt the computation that's acquiring the resource, because you might just succeed in acquiring it, but fail to return it, and then it gets interrupted. So that's equivalent to leaking resources. So you have a very strong runtime level guarantee that those will not be interrupted. Neither acquisition nor release, they'll never be interrupted. If release succeeds, then release will, or if acquire succeeds, release will always be invoked. And release will always be invoked even in pathological scenarios. For example, bracket nested in bracket. And you interrupt down here, well then you have to run the release here. The release here, it could error out. It could fail to release. If you wrote a really bad release function, it could fail. It could throw an exception. That will still not prevent the outer brackets release from being invoked. Here's an example of how you would use this in practice. You open a file and you bracket it with close file, and then in between you use the file and do whatever you want with it. So you use this primitive, and suddenly you don't have to worry about resources anymore. The final combinator that we're going to talk about is called Supervised. And Supervised does something pretty novel. You call it on a big old block, big I/O of A. And what it does is it will, after that I/O of A terminates, finishes, any fibers you forked inside the body of that will be terminated. In other words, say you're building a web server, and a request comes in, and you're doing a bunch of stuff. You know, you can't even keep track of all that stuff. But you want to make sure when you close that socket connection, nothing survives. You didn't forget to clean up any fibers. Then it's as easy as calling .supervise. And then all the stuff that you forked off, they'll all be cleanly shut down and resources will be released. So I'm running out of time here, so I'm going to wrap this up pretty quick. But I do want to briefly cover the fact that there are algebraic laws that underpin many of the abstractions that I've just talked about. I don't have time to get into all of them, but there's so far we've found 12 laws, and actually the semantics of our program, or of how we're implementing this, have actually changed based on our ability to write laws. Sometimes we were like, we can't, we want to write this law, but we couldn't because the implementation didn't permit that. And so we changed the implementation, and then it just suddenly things started clicking. So I will tell you this, that first off, algebraic laws, they are the way that you reason generically about powerful abstractions. And a lot of these things in Scala Z8's I/O, like fork and join and so forth, supervised even, they do have semantics, and they actually have algebraic laws in some cases, and then in worst cases, operational laws. And that's very, very, I think, important and critical when you're trying to abstract over these things, that you be able to reason about them generically. All right, real quick. The section you're all waiting for, right? Performance. Okay. So what I want you to do is go to your boss and tell her or him that future is just not practical. It's like future is too ivory tower. You need something more pragmatic. You need Scala Z8's I/O. Because Scala Z8's I/O is up to 195 times faster than future, and has all these amazing guarantees about resource safety and so forth. So you should go to your boss or your team and you should say, look, we can't use future anymore. It's just not getting the job done. We need to switch to pure functional programming. That's the only thing that's practical for the job. Scala Z8 I/O is, at least in the benchmarks that I have created, is consistent, right? We're going to find out if that's true in a second when I switch tabs, if I actually know what I'm doing. is consistently faster than everything else out there, and in some cases by a not insignificant margin. And I'd love to be able to spend time talking about the optimization techniques, but we won't have. Operations per second. However, usually one of these bundles thousands or tens of thousands of operations inside there. So this is like really hundreds of thousands or millions of operations a second. Yeah, and every one varies, but they're all ops per second, and higher is always better. So safety. How about like day-to-day stuff? Scala Z8 has stack safe safety for synchronous and asynchronous code. It has that bracket primitive, which gives you strong guarantees about resource usage. No implicit executors anywhere. And no mutable implicits. A very clean API. There's nothing, there's no implicits anywhere. No implicits, and you don't feed mutable stuff into anywhere except the methods that capture effects. Expressiveness, Scala Z8 has not a very large set of combinators. We looked at them all. In fact, we looked at not just them, but stuff we derive from them. And we saw that, like, without exception, they're composable. We can build things on top of them. We can build really complex, powerful stuff on top of these small set of things, and they solve the real-world problems that you have, that I have, and that your business has, and they solve it in a way that you, as a functional programmer, can appreciate. What about FS2? Well, first off, if you turn to FS2 to get resource safety for an I/O monad, then, because I/O is not a stream. I/O produces one value. Streams produce 0 to many value. A stream library is not the place for these strong guarantees. It's an I/O library. And I think FS2 has to, compensate it. It hasn't been able to rely on rich primitives like this. So it has like all this stuff baked in. It has an actor library, it has an FRP library, it has an MVAR implementation. It has concurrency primitives, which are, in some cases broken, like, race and bracket and fork and join, all this stuff in here. It's a sign a richer semantic basis is lacking. It wasn't able to build what it wanted to build, so it had to build all this extra stuff just so it could build a streaming abstraction. And that shows, like, this race combinator here, which takes two f of a's and races them, it's broken. Like, it's broken. It's going to return the first one, and then that other one is going to keep executing, doing all of its effects, sucking up CPU and memory and socket connections and transferring huge amounts of data. That's broken. And I think, like, as functional programmers, we can't keep ignoring this. We have to solve the real-world problems that developers have every day, that the business has, if we want to go mainstream. And that's what I'm trying to do in Scala Z8, and I hopefully inspire some of you to do in your own libraries. And there's nowhere where this sort of brokenness is more apparent than in FS2's implementation of MVAR. So they had to add a time to get to it. So there's ordinary take var, and then they had to add a timed version of that. That is the definition of non-composability. In FS2, or in Scala Z8, you just call take var. And if you want to time it out, you just time it out. Why couldn't they do that in FS2? It's because if they did it, they would leak resources. They would hold on to callbacks. And that would interfere with the queue of putters or takers, and it would break the program semantics. So they had to introduce a separate method there. This shows you the power of composable functional programming. Like, these MVARs, they don't know anything about timeouts. They just do what they're supposed to do, and then we add timeouts on top, and it doesn't have to be just take var, it could be put var or anything else in the world. Just call timeout on it. That's the power of composability. So we are totally out of time, and I wanted to give a special thanks to ScalaIO for inviting me to speak here, and Valentin, who was there. He ran away. Oh, there he is. Thank you, Valentin. And also Alex Nedelq. I studied Monix in the early days, and thanks to him, I came to the insight that in order to have a super fast I/O monad, your interpreter needs to have a zero allocation happy path. No heap allocations. And once I had that insight, I had a breakthrough that enabled me to get really good performance. But I got that insight thanks to the work that he's done in Monix. So I'm very grateful to him. And also Daniel Spiewak for the work he's done on Cats.io, especially trying to give us ways to reason about these effects using algebraic and operational laws. Very important work. And then thank you all for coming to ScalaIO. This is a nonprofit indie conference, and I'm just so happy that you came here to network and to see these talks, and also to support a nonprofit indie. So thank you very much for coming here and seeing my talk today. Thank you.